Read B part one for me. Let's do the questions quickly.
A carter is pumped to a pressure of 2 by 10 to the power of 5 Newton meter squared.
Wait,
In the mo-
anytime you see this notation,
mm,
another way you could write that is Newton per meter squared. So instead of saying nm minus 2, you could say Newton per meter squared.
all
Anytime you
right,
see a negative power, that means it would have been the denominator. So you'll say per. Right? Continue.
right. In the morning, when the temperature is 23 degrees Celsius, later in the day, the temperature rises to 34 degrees Celsius. Calculate the new pressure in the tire. The volume of air is kept constant.
All right. So let's underline the key information, right? So they are giving us a pressure, right? We could call that the initial pressure. Let's call that P1. So P1 is equal to 2 by 10 to the power 5 Newton per meter squared. Great. And this is the pressure when the temperature is what?
23 degrees Celsius.
Now talk to me. In physics, specifically in these calculations, can we use the temperature in Celsius?
Now I need to convert to Kelvin.
Right, and we would have discussed why in the last class, right? If you use Celsius, then it will not be directly proportional, right? You actually have to shift the graph. You actually have to shift the graph, right? And you have to actually start from minus 273 and then call that 0. That's the only way it's going to be directly proportional, the relationship. So you have to convert all the temperatures to Kelvin. So what would you do with 23? What would you add to it? You remember how to convert Celsius to Kelvin?
You say at 273.
Right. What would you get?
So what is it?
What would you get?
Oh, 296.
Okay. And then they're saying later in the day, the temperature rises to 34 degrees Celsius. So I would consider that to be my first temperature or my second temperature.
The second temperature, so
Right. Again, we don't work in degrees Celsius. You need to convert that to Kelvin. So that's going to be 34 plus 273. Somebody answer first. 34 plus 273.
307.
307. Right, and that'll be Kelvin. Now, they want us to calculate the new pressure of the tire. So what is unknown here is P2. P2 is the unknown. Is there any law that you all know of that has pressure and temperature in it? Talk to my guys. And if you could remember, what law is that?
Pressure.
Is it pressure law?
that's the Lossac law,
Say that again.
the the
Yes.
pressure law.
Yes. That is Gay-Lussac's law. Right? So what is the law? What does it look like? Talk to me, Zachary. What is the pressure law?
So that one is the something if like a gas at a constant volume, the pressure is directly proportional to the temperature.
Mm, okay. I hear what you're saying, right? I hear what you're saying. But I want the formula. I want the formula. I want the formula.
So P1 over T1 is equal to P2 over T2.
Right. And would you guys say that these two are inversely proportional or directly proportional?
Directly.
And let me call somebody, Adil. If I increase the temperature, what happens to my pressure?
There rise?
Yeah, it rises. So is Zachary correct? He says it was directly proportional.
Yes.
Yeah, he was correct. Great. So Zachary, let's do substitution now. So P1 is 2 by 10 to the power 5. Great. All over T1. T1 is 296. And that's going to be equal to P2. I don't know what P2 is, so I'm going to leave that blank for now. And T2 is 307. So Zachary, can we see that there's a fraction on either side?
See if it's a one on either side.
A fraction on either side.
Yes,
Can we
sir.
see that? So anytime you have a fraction on either side, you could find the what? Well, you could do what on both sides. So that's what C. You could C. I'll give you a hint. So I'll multiply that.
So cross multiply.
Right, I'm gonna cross multiply. I want the unknown to be on the left-hand side, so I'm going to do the multiplication involving P2 first. So that's gonna be 296 P2 equals to what, Zachary?
2 by 10 to the power 5 by 307.
Nice. And for me to find my final answer, what would I need to do on both sides? Keep in mind, I want to find for P2. Right
Divide
now,
by
right. You see it. Divide by,
296 on both sides to get P2 by itself.
correct, because right now P2 is being multiplied by 296, so like you had to cancel that off. Great. So I want somebody to plug that into your calculator. What's it? Calculator, and let me know what you get. And I would like you to tell me the units as well. If you don't tell me the units, you're gonna lose a mark. You're not gonna get 5 marks. So to call for this boy, Nikolai. Hey Nikolai. My partner reach. Nikolai, you good?
Yes, I good.
Nice. Nikolai, plug this into your calculator and let me know what you're getting for P2. Right.
For P2, so I get 2.07 by 10 to the power 5 newtons meter negative 2.
That's so incorrect. Because when I plug it into my calculator, I'm getting 207,432.4324. Right? And the units for that would be what? What is the units for that? What was the unit for the initial pressure?
Newtons per meter.
Newtons per meter squared, because it was m minus 2.
Oh,
You can write newtons slash meter squared, or you could write nm minus 2. Now, look at the form in which they gave us P1. They gave it to us in standard form. So we should write our answer in standard form as well. So to do that, I'm going to take my decimal place and shift it right before the 2. So 1, 2, 3, 4, 5. So that's going to be 2 point. That's going to be 2 point what? Right? So that'll be 2.07 by 10 to what power?
5.
Right. And you put the units. I'll stick to 1 for now. Okay, is there anybody that did not understand this question at all? Talk to me. Tell me no. Nabil, Nabil, you there?
Yes, sir.
All right, so Nabil, looking at your working, right? Um, I see that you wrote 20 by 10 to the power of 5.
So that was at 2.0.
That is 2.0. Okay. Oh, and I didn't see the point. Okay, yeah. Yeah, the answer you have is correct. Right? All right. Is there anybody confused by this? Let me just do a roll call. Adil, Karina, Zachary, Drew, Shayna, Nabil, Ambika, Nikolai. Talk to my guys. And is anybody
Okay.
confused?
No, sir. So I did it.
No, sir.
But I didn't cross multiply and change the formula.
You just multiply by 307.
Yeah.
Yeah,
But yeah.
I would do that as well. But like most students, when they look at this, they know immediately to cross multiply. Everybody just, I know most people just prefer this, but that's
I
easy.
prefer changing the formula. I don't know.
I prefer to multiply by 307 as well because they get the answer one time. It cancels off here and it gives you the answer one time. Right. So Ambika, Nikolai, um, talk to my guys. What's going on?
I understand.
All right, Ambika, you know, wake up.
No.
No, okay, okay. I hear everybody's sleepy voice. I hear everybody have a sleepy voice. Yeah. All right. So Ambika, since you're unmuted, help me with part two.
The increase in pressure would happen because the increase in the temperature would cause the air molecules in the tire to gain kinetic energy.
Right. As a result, they would start vibrating at a faster rate, hitting against the walls of the tire. And that would contribute to the pressure increasing because the air molecules gain kinetic energy, so now they can move about and hit the walls of the tire with a greater force. You have to say all of that too. So say back your answer and I'll add the part to it. So say it again.
The increase in pressure would occur because
Right? So
um
so when so we could write, so you want to be very concise in our answer. They're asking us to explain why the increase in pressure occurred. So we already know that the pressure is going to increase. So you could jump straight to your answer. So you could say when the temperature is increased, talk to me. The what? The
the air molecules
mm-hmm,
would gain kinetic energy, therefore it would vibrate.
energy causing them to
Vibrate.
out frequently. As such, it would hit. Alright, so when the temperature is increased, the air molecules gain kinetic energy, causing them to vibrate and move about more frequently. As such, they would hit the walls of the tire, exerting a force, thus increasing pressure. Let me know if you understand that or not. Zachary, when you add heat to a gas, does the gas expand or does it contract?
It is expand.
Right, but why? Well, when you add heat energy, the molecules gain kinetic energy and they start to move about more frequently with a greater force. And if it's in an enclosed space, think about it, Zachary. Wouldn't the molecules want to expand or wouldn't they push against the wall with a greater force? Because,
Yes, sir.
right. So I hope you understand the answer. Ambika, you understand the part where you had to include about it hitting the wall and that would actually increase the pressure?
Yeah,
Because
I understand.
remind me, what's the formula for pressure? Pressure is tell me, Ambika, what's the formula for pressure? Pressure is what over what? Can I hear an Ambika? One of you all could volunteer. What is the formula for pressure? Formula for pressure is does anybody remember the formula for pressure?
Temperature over volume.
No. I give you that hint. Pressure is equal to force all over.
Temperature.
Area.
Area. Right. So what happens here is that when you add energy to the molecules, they start to move about more and at a greater velocity. And so now the molecules have the energy to hit against the walls with a greater force. So according to the formula here, if the number on top gets bigger, what's gonna happen to my answer? If the number in the numerator gets bigger, what happens to the final answer? Does it get smaller or bigger? Take for instance, if I had 10 over 1 versus 100 over 1. By me increasing the number on top, did I get a bigger answer or a smaller answer? Nikolai, tell me fast, what is 10 over 1? What would that be equal to? 10 over
10
1.
over 1 and
Yeah,
then
where's 10
10
over? 10, right? Where's 100 over 1?
or 100.
Right, so Nikolai, if I increase the force, but I keep the area the same, what's gonna happen to my pressure?
It go increase.
Exactly. So when the molecules gain the kinetic energy, they are now moving about more frequently. And as such, they're gonna hit the walls of the balloon with a greater force. They're gonna exert a force on the walls. And if the force is getting bigger, then your pressure is going to increase. Hope that makes sense. Ambika, Sheena, Zachary, Nikolai, Nabil, Adil, talk to my guys. I'm gonna follow ready to move on. Do you all understand this properly?
Yes, sir.
Okay, great. Yeah. Oh, let's show. I feel like everybody's so quiet today. And Karina, yes, I see the profile picture. But I feel like that's not an effective mask. Still get everybody sick. Sheena, you see the mask?
Yeah, I think it's a good enough profile picture.
Oh my goodness.
Why it looking like Voldemort so?
I think that
That's the point.
I think that the community is suffering, like the whole class would dwell in some sickness for a while.
I feel so. Everybody like real dead today. Like it's a zombie apocalypse or something. Alright? Okay. Sheena, help me with part 3.
Yes, sir.
So give part 3 a read for me.
Calculate the ratio of new volume to old volume, V2 over V1 for the tire if the pressure is held constant while the temperature rises from 23 degrees Celsius to 34 degrees Celsius.
Okay. So we talking about volume and what here? Talking about volume and
Pressure.
what? Right. No. No. What parameters here changing? So,
Or the temperature and the
right.
volume.
If you notice, what they say about the pressure?
It's rising.
Nah, nah. Check it out.
Oh, sorry. Crap. It's held constant.
Right. So if the pressure is held constant, then what are the other two things that are going to change?
The volume and the temperature.
Exactly. Exactly. So volume and temperature are changing. All right. Does everybody understand that they're saying the pressure is held constant? So if it's held constant, is the pressure changing?
No, sir.
Nah, the pressure not changing because it's being held constant. So we're looking at something with volume and temperature in it. Are there any formulae or formulas that have volume and temperature in it?
Charles law.
Exactly, Charles law. What does Charles' law say?
V1 over T1 is equal to V2 over T2.
Right. Okay, great. Now we want to calculate the ratio of the new volume to the old volume. So we want to write this in such a form such that what is on the left hand side is V2 all over V1. That's what we want. That is what we want to do. It's gonna be a bit tricky, but I believe we could figure it out. Right? So Shina, we want to make V2 over we want to make this a subject of the formula. Do you have any suggestions as to how I could do that?
Make it up. First time. I want to look at them before I talk.
So we want to make V2 over V1 the subject of the formula. Right, so Shina, we can figure this out, right? Shina, if we want to make this the subject of the formula, um, I want you to locate where V2 is. Where's V2? Where's V2? On the left hand side or the right hand side?
The right hand side.
All right. So let's work with the right hand side. We already have V2 where it needs to be. Talk to me. Should T2 be over here?
No, sir. You can multiply on both sides.
Right, so I can multiply both sides by T2. Talk to me, guys. I don't just want to hear Shina. Right? Drew is a math boss. If we're trying to make V2 over V1 the subject of the formula, we could already see that V2 is in the numerator. But in my final answer, V1 should be in the denominator, not T2. So Drew, doesn't it make sense for me to get rid of T2 by multiplying by T2 on both sides? Talk to me, Drew. I'm if you understand.
Yeah.
Okay. Adil, I need to see if you understand this. So Adil, we want to figure out the ratio of the new volume to the old volume. So we have to make V2 over V1 the subject of the formula here. That is what we need to do.
Yes, yeah.
So Adil, if you look at the right hand side, you see in V2 is over there. But
Yeah.
it should be over V1. So if it should be over V1, should T2 be over here?
No.
No, T2 should not be over there. So this is what I'm going to do. I'm going to multiply both sides by T2. If I multiply both sides by T2, wouldn't it cancel off over here?
Yeah.
It would cancel off over there. And on the other side, it multiply. So you're now going to get T2 V1 all over T1. And that is going to be equal to V2 because the T2s would cancel off. Are you lost?
No.
No? All right. Okay, so Adil, we got rid of the T2, right? So right now we only have V2. However, we need to get it over V1. So if for me to get this thing over V1, what would I have to do on both sides?
Divide by V1.
Yes, I would have to divide by V1 on both sides. If I were to divide by V1 on the left-hand side, what's going to happen?
They will cancel off.
It will cancel off. Exactly. So then my answer is going to boil down to T2 over T1 is equal to,
V2 over V1.
right. Is there anybody that did not understand this at all? I know like the maths are a bit confusing. So I need to tell them if they don't understand it. Nikolai, talk to me. Talk to me.
Nah, I understand it.
Yeah, sure.
Yeah.
Okay, taking a word for it. So, Nikolai, in other words, V2 over V1 is going to be equal to T2 over T1. Do we know what T2 and T1 is?
Yeah.
All right, so what would T1 be?
T1. T1 will be 23.
Right, but could we work with the 23 degrees Celsius? Could we work with
Now, I
Celsius?
convert to Kelvin.
Right, you have to convert that to Kelvin. So how would I convert 23 degrees Celsius to Kelvin?
Add 273 to it.
What would I get?
You get 296.
What is the second temperature?
34 degrees Celsius.
So what would the second temperature be in Kelvin?
307.
Is everybody all right with that? I don't like how he's so quiet today, I don't know what's going on. What is this? What is this? What? Olha, I'm gonna call Ian Allen for you. I don't understand why everybody's so quiet. Like I feel like it's the morning syndrome or something, like everybody just sleepy oh. And then too. Um Karina. No, not Karina. Sheena. Get everybody sick. Sheena get everybody sick. So I think maybe
Excuse.
that's why.
Oh my goodness.
So Sheena, now that
Yes.
I have T2 and T1 in Kelvin, how am I gonna find my answer for V2 over V1? Well, we know that V2 over V1 is actually
Is
T2
equal
over
to,
T1.
yes,
So what is T2?
307 degrees. I mean Kelvin.
And what's V1?
296.
Right, so plug into the calculator and let me know what you're getting to two decimal places.
One point zero four.
Say that again?
1.04.
Right. That's it. Let me know if you guys understand that. So we wanted to calculate V2 over V1, right? V2 over V1 is 1.04. So in other words, V2 is actually 1.04 by V1. That's the ratio. So it's like a 1 to 1.04 ratio. I know you're looking a bit confusing. I know. So I need to tell me if I'm confused. Mika, we feeling cooked or like we like okay, be honest with me. Be like very honest with me. I need to know if we cooked.
No, not really.
Not really? Okay. I see Danelle join. Danelle, how are you? You good? How are you this fine Saturday morning that feels like a morning to sleep? How are you?
Yeah, hi, sir. I'm paying attention, but I'm on my way to another class. So that's why I'm not like answering often.
Okay, no problem. Right? Well, it's good to have you. If at any point you feel confused, just tell me, right?
Okay, yes, sir.
All right, so before I move on, I just want to do a quick recap just to make sure that we have everything locked in. Like, very quick recap. Today we're going to start lenses. Well, we've done optics now. All right, adults, we're going to start lenses. Right. So, Zachary, I want you to tell me, what is Boyle's law? The formula.
Say Boyle's law.
Yeah, Boyle's law.
Um,
I'm putting you on the spot here.
yeah, so hold on. So that's the one with P1, V1 is equal to P2, V2.
Yep. And in this, for this law, what is held constant? What is held constant?
Gas, the mass of gas.
Yeah, the mass is, well, technically the mass is constant for all of them, right?
Oh,
All of
yeah.
them. So we also looking at pressure, volume, and temperature. So what is held constant other than mass?
Pressure
Now, if pressure is in the formula itself, then that cannot be held
or
constant.
temperature, so
Yeah. Right? And let's just go back to the definition so you'll see what I'm talking about. Should be here. Yeah, watch. Look what it says. Give it a read.
for a fixed mass of gas at a constant temperature, the pressure is inversely proportional to the volume.
So you see that, right? A fixed mass of gas at constant temperature.
Right, so
Right? Because think about it. When two of them are changing, one of them needs to remain constant. So the constant here is the mass and the temperature. And talk to me. Pressure and volume, they are what to each other? Proportional or inversely proportional?
inversely proportional.
Right. And what does that mean?
So the graph wouldn't be a straight line.
Well, if you plot P versus V, it would not be a straight line. But if you plot P1, I mean what's saying, if you plot P versus 1 over V, then that would be a straight line.
Yeah,
Right? Now this means that if you increase the pressure, what happens to the volume?
it would decrease.
Right, great. So what I'm doing here, I'm just putting a summary note. So if you have an exam or something, you can just look at this quickly and you have all the information you need. Right. Let's move on to Charles' law now, or Gay-Lussac's law. I spelled the man name correct. Right. So Nabil, what is Gay-Lussac's law, also known as um pressure law? This is pressure law.
It's like when the temperature increase, the pressure will increase also.
Right. Right. So in that case, it will be directly proportional. Directly proportional. So directly proportional. And if it's directly proportional, right, we know that if the pressure increases, what happens to the temperature?
It increases also.
Yeah. But the easiest way to understand this is if you increase the temperature, pressure will increase, right? Great. So if we're dealing with pressure and temperature, what do you think is the constants?
Volume.
Right, mass and volume. You okay?
Yes, sir.
And now we need to write Now we need to write the formula for that. So it's gonna be what?
P1 over T1 is equal to P2 over T2.
Great. So right? And Ambika, I want you to tell me what is the other gas law?
That's Charles' law?
Right. Do you like Charles chocolates?
No.
Real. If somebody gave you Charles chocolate for Valentine's Day, don't them.
I don't really care that much.
Mm. Okay. It's not that deep. It's not that deep.
No, not really.
But like, I feel like if somebody gave you Charles chocolate, I don't know, like, I feel like Charles chocolate just something about it off. The mocha one is tastes good though, like the coffee one. That one is tastes fine. That one is tastes fine. Oh, you know about Goldfinger? Oh, you know about that? Like the red packaging with like the gold text on it. Oh, you know what I'm
So
talking about?
yes, sir.
Yeah, that is Lash. That is Lash. That's one
Um,
chocolate product that's Lash. That
I
is
bought one the other day, and within a matter of like 5 minutes, not 5 minutes, like 15 minutes of walking into Chigona's, it melted in the pack. So I had to like go home and freeze it.
Wait.
It was that hot the day before. It was yesterday actually.
Yeah, well, these days it's crazy hot. I don't know why. I have no idea why this hot. Right? So Ambika, let's continue. Charles Law. What does Charles Law say?
That gas is at a is constant. No, wait, pressure is constant, my bad.
Right? So the constant here is mass and pressure. For all of these, you must have a fixed mass of gas. Right? So the only thing that should be changing is these two variables. So mass and you said pressure? Yeah,
Yeah,
pressure. And this relationship, would it be proportional or directly proportional? What's saying?
directly proportional.
I meant to say, would it be directly proportional or inversely proportional? Right? And the answer,
Directly.
right. Great. And so in this instance, if you were to increase, the volume, what would happen to the temperature?
Mm,
Maybe we should look at it the other way around, right? Imagine a hot air balloon, right? As you increase the temperature of the gas, what happens to the volume?
It it grows like you gain more. I guess like that makes sense.
Yeah, Ambika, when you heat up a gas, we just discussed that the molecules are going to gain kinetic energy. So now they're going to exert a force on the walls. And if they're exerting a force on the walls, wouldn't they push the walls outwards?
so volume would increase as well.
Yes. Right? So we're dealing with temperature and volume. And you would notice that anytime it's directly proportional, it's written as a fraction. So what is Charles law going to be?
V1 over T1 is equal to V2 over T2.
Great. Are you all okay with this? Let me know. I find me too quiet today,
Yes, sir.
I can't understand the
Yes, sir.
silence.
Yes, sir.
I can't understand the silence, right? And talk to my guys with Boyle's law. If I were to plot a graph of say P versus V, since it's inversely proportional, would I get a straight line?
Nah, sir.
Nah, I would get this, right? Because with this graph, if one of them increasing, the other one decreasing. Okay. However, if I had a graph of, say, if I now had a graph of P versus 1 over V, how would that graph look?
So that would be a straight line.
Right, that would be a straight line. Okay, so that's that for that. Onto this one now. Oh, and if the graph is P versus V, well, forget about that. Now you would have to find the equation of the line and differentiate to find the gradient at every single point since it's a curve. So they will never do this in the exam. They're not that wicked. But if you have a graph of P versus 1 over V, what will the gradient give you? So remember how this is go, right? You'd write pressure is proportional to 1 over V. And then in the next line, you would say P is equal to what? Remind me. When you replace the proportional sign with an equal sign, what's the next line? You have to introduce the what constant or what? The constant of?
Yeah.
The constant of proportionality, K. So when you look at it like this, right, it's really P is equal to K multiplied by 1 over V. That is what it is, right? So like, talk to me, what do you think the gradients would give you? If I plot P versus 1 over V, look at this. This is exactly uniform y is equal mx plus c. I can write plus 0. If you understand the straight line equation, you would understand that y is what's going on the y-axis. So can we see that pressure is on the y-axis? Yeah or no? Some of you could see that. Pressure is on the y-axis.
Yes, sir.
Okay, what is the gradient giving us? M is
K.
giving us what? M is giving us K. And what do we have to plot on the x-axis?
1 over V.
You see it now, right? You see it now with your own eyes. And the line is passing through what?
The origin.
Right, because the y-intercept is 0. So you see now for yourself too. It passing through 0, comma 0. So long story short, if you have a pressure versus 1 over V graph, the gradient gives you the constant of proportionality, K. Great. Let's move on to this one now. So this is directly proportional, so it's a lot simpler. If I plot a graph of pressure versus temperature, I'm expected to get a what kind of graph? A curve or a line? Tell me, guys. So it's
A
directly
line.
proportional. A line, right? It's directly proportional. Think about what a line means, right? So Shana, as you can see, as the temperature increases, what happens to your pressure? We could see that it increasing as well. That's what a straight line means,
Yes, sir.
right? So Shana, what would the gradient give you for this graph? So just run back through the scenario, Shana. You would say pressure is proportional to temperature. Then you would say P is equal to what?
So over here.
Say that again?
Well, P will equal to K times T.
Right. And if you compare that to y is equal mx plus c, I can put plus 0 over here. You'll see that P is on the y-axis. T is on the x-axis. The y-intercept is 0. We're seeing that. And the gradient will give us K. We could see that.
Yes,
We
sir.
see all of that. So the gradient gives K. Awesome. On to the last graph that I need to know. This is pressure. What's in? Right, so this is volume and this is temperature. Since it's directly proportional, volume and temperature, this graph, what would it be? Would it be a curve? Should not inverse proportional relationship, or would it be a line? Should not directly proportional relationship? Tell me, Adil. Here, Adil.
So it's
Zach,
a straight line.
it would be a straight line, right? We know that. It would be a straight line because when one increases, the other one increases. And what will the gradient give you?
K.
Right? Gradient gives K. Nice. So you all could take a screenshot of this. This is a summary of everything that we did. And we need to write something in red. There's something very important here. Whenever you're doing these calculations, the temperature needs to be in what?
Kelvin.
Kelvin.
Yeah, the temperature needs to be in Kelvin, otherwise you're not going to get a correct answer. Please remember that. Right, and to get Kelvin, I need to add degrees Celsius to what? Whatever the degree Celsius is, we need to add it to what? Talk to me.
273.
273, right? Great. The only other thing that you should know is the combined gas law. I don't really see it coming often, but you do need to know it. So, Shina, as its name suggests, it says combined. When you hear the word combined, what do you think of?
Altogether.
Altogether, right? Combined gas law. So I'll write down the combined gas law first, and then I'll show you how to prove it. So the combined gas law is P1 V1 all over T1 is equal to what? You take a guess.
P2 by V2 over T1. I mean, T2, yeah. So
Make
you
a
have
mistake.
T2, yeah.
Yeah. Great. Now let me show you guys how to prove this quickly. So Shina, I want you to tell me the three gas laws very, very fast. What are the three gas laws? So we can start off with
So I want
boiling.
the names, I want the formulas.
Formulas. So P1 V1 is equal to P2 V2. Tell me the other one.
Yeah, V1 over T1 is equal to V2 over T2. And T1 over T1 is equal to P1 over T1 is equal to P2 over T2.
Okay, you okay with this, right?
Yes, sir.
So let me show you something. What would happen if I made V1 the subject of the formula here?
What happens if we make V1 the subject of the formula?
Yes.
You'll end up with V2 by T1 over T2.
Right, so V1 will be equal to V2 all over T2 by T1. Right? You'll see where I'm going with this. If I were to make V2 the subject of the formula here, V2 would be equal to what? So
T1.
I'd have to multiply both sides by T2.
Yes, sir.
So that'll be V1.
V1 by T2 over T1.
Okay, great. So what I'm doing here is I'm trying to write what V1 is, V2 is, using this law, right? And this is Charles' law. So I know that V1 is equal to this. I know that V2 is equal to this. Great. Now I need to figure out what P1 and P2 is. What is P1?
P1 is P2 by V2 over V1.
So P1 is equal to P2 by T1 all over T2. All right, what would P2 be equal to? P2, what would P2 be equal to?
P1 by V1.
Nah, P1 by T2,
Sorry.
right? P1 by T2 all over T1. Nice. And now I'm going to plug it. Now I'm going to plug all of this into this. Right? P1 V1 is equal to P2 V2. So instead of writing P1, I'm going to write P2 T1. I'm going to write P2 T1 all over T2. And V1 is this is supposed to work out, right? So that'll be V2 T1 all over T2. That's going to be equal to P2, which is right multiplied by V2. And we know that V2 is V1 T2 all over T1. Right. So Shayna, let's continue. So Shayna, let's multiply this out, shall we? If we multiply this out, what are we going to get?
Sorry, sir. Right.
So I'll get P2, right? P2 by V2, and you have T1 by T1. That will be T1 squared. And in the denominator, you have T2 by T2. What is T2 by T2?
T2.
That'll be T2 squared. Right? And then tell me what we get on the right-hand side.
P1 by V1 by T2 squared over T1 squared.
All right. We're very close to getting where we want to be. Okay, so you want to get P1 V1 over T2. I mean P1 V1 over T1, right? Supposed to get the answer. Let me think. Okay, so this is what we're gonna do, right, Shayna? Does the T1 squared belong over here? Look at the formula we're trying to prove. We're trying to prove P1 V1 all over T1 is equal to P2 V2 over T2. That's what we're trying to prove.
No, sir. It
So
is
it
not.
shouldn't be over there. Like, if we're trying to make it look like this, shouldn't be over there. So what I could potentially do is I could divide throughout by T1 squared to cancel this off. But then we're still gonna end up with a square. Let's trust the process and see how it goes. So I'm going to divide both sides by T1 squared. And if I do that, I'm going to end up with P2 V2 all over T2 squared. And that'll be equal to P1 V1 and but that's gonna be troublesome. That's gonna be troublesome because now you're gonna end up with T1 to the power 4. I think I'm proving something else as opposed to the combined gas law. Because it will not work out from what I'm seeing here. Because if you do that, it's gonna be P2 V2 over T2 squared is equal to P1 V1 T2 squared all over T1 to the power 4. And that's no bueno. We don't want that. We do not want that. Okay, so I'm gonna put asterisk by this. Something is wrong here. But it's supposed to work out. Let me just recalibrate and think. Okay, Shayna, let's try something else. What if instead we were to make P1 and V1 the subject of the formula here? So Shayna, we're going to try something quickly, right? So Shayna, try to stay unmuted so we can run through this. And everybody else, I will explain it when we get the answer we're supposed to get. Right now, we're just running through a couple obstacles. So Shayna, make P1 the subject here for me.
P1 will equal P2 by V2 over V1.
Let's do this quickly to see if it's going to work out. All right, that's P1. All right. Okay. In all instances, I'm seeing some trouble. If you do that, okay, and then you would say P2 V2 all over V1 all over T1, right? And then that would be equal to P1 V1 all over V2 all over T2. I just checking something quickly. And that'll be P2 V2. Right, that'll be P2 V2 all over V1 multiplied by T1 equals to P1 V1. Yeah, in all of these derivations, I'm seeing a problem. Seeing a problem in all the derivations. Weird. I'll put an asterisk by this, and I'll derive the proof after class. But to get the combined gas law, you have to use these formulas to get it. I know that much. That's where it comes from. This thing like upsetting, man. I'm gonna try one more thing before I move on. So another way we could write this is V1 T2 is equal to V2 T1. Another way we could write this, Nikolai. I tried something else before we move on, right? So Nikolai, I want you to observe how I wrote this, and I want you to write this in the same form. So if I'm cross multiplying, how would I write this? If I'm cross multiplying, how would I write this? I'll start you off. That'll be P1 by Nikolai. Let me know if you're there. Can I hear Nikolai? Drew, you there?
Yes, sir.
Okay, Drew. Let's try cross multiplying this, right?
Mm-hmm.
So if I cross multiply that, I'm gonna get P1 by T2 is equal to what?
P2 by T1.
Great. Now, I want you to notice that in both of these cases, we have T2 and T1. So what would happen if I made T2 the subject of the formula here? What would happen if I did
And
that?
the one on top,
Yeah, the one on top.
you divide both sides by V1.
So that'll be V2 T1 all over V1. Okay. I keep noticing a problem. Because if you do that now, and you plug it into this, that's gonna be P1 by V2 by T1 all over V1. Okay. And let's try to do that for the other one. Suppose you make T1 the subject of the formula. What would that be equal to for this one? If you make T1 the subject of the formula.
V1 T2 divided by V2.
Right. If I were to plug that in, that's going to be P2 by V1 by T2 all over V2. What I could do over here, I could, but if I If I do that, the V2 is gonna cancel off. If I divide both sides, no, you're gonna get V2 squared. I'll put asterisk by it for now. I'll put a pin on it. Because all the derivations are ending up we're getting a squared somewhere, and it's just recursive. But for now, just remember that this is the combined gas law. Right? Right, so is everybody okay with the summary for the three gas laws? Let me know if you guys okay up to this point. The summary for the three gas laws.
Yes, sir.
Okay, no confusion there or like I'm gonna. Amika, you have any confusion here with respect to the three gas laws? I need to hear from everybody. Nikolai, you there?
Yeah.
All right, Nikolai, you have any confusion when it comes to the regular three gas laws?
Nah, I don't have no confusion to it.
Okay, cool. And this is the combined gas law. In the combined gas law, the only thing that is constant is the mass, but everything else is changing. So the only thing here constant is the mass. So remember that's combined gas law in case it comes. So finally gonna wrap up with thermal physics, as if for thermal physics. Now we're gonna move on to waves and optics. Finally. So Zachary, I want you to start off by giving wave features a read for me. Give that a read.
Waves carry energy without carrying matter. Some waves must propagate through a medium. They involve oscillations, where they can be just one oscillation called a pulse, or a series or succession of oscillations called a progressing wave. Waves that require a medium to be transferred are termed mechanical waves, while those that can travel through a vacuum are classed as electromagnetic.
Right. So Zachary, let me try to understand what we're reading, right? So a wave carries energy. Does that make sense? Think of a sound wave. Does a sound wave carry energy?
Yes, sir.
Okay. Think of so I go on to think of. Think of infrared waves. Do you know what infrared waves are?
So that's from the sun.
Yeah, infrared is from the sun. That's the heat.
Yeah.
Doesn't that carry energy?
Yes, sir.
Does it carry matter though?
Nah.
No, it doesn't. It just floats through the air, right? It just passes through the air. Some of them need a medium to be transferred. Some of them could just be transferred through the air. So it does not carry any matter. I'm talking about like physical matter. It doesn't carry matter, but waves carry energy. Some waves must propagate through a medium. Zachary, if you took your ears and you placed it, you probably do this when you was bored in primary school. Yeah, wouldn't you take your ears and put it against the desk and you might probably hit the desk? That ever happen?
Yes, sir.
Yeah, and when you hit the desk, do you hear the sound?
Yes, sir.
So like the sound was propagated through a medium. The sound waves were carried through a medium. In that case, the wooden desk. Right? So they involve oscillations where if it have just one oscillation, they call it a pulse. When we move on to the graph, you'll understand what I mean by an oscillation. But an oscillation would be like one full cycle. Like you're starting from rest, you go into the maximum, and then you're coming back at rest. Did you all ever do the pendulum labbers yet? Did you all ever do the pendulum labbers yet? Do you know what I'm
So
talking
So
about?
what's
we
the
didn't do the
pendulum?
lab yet, but we went through it.
Yeah.
Okay. So what would a full oscillation look like for a pendulum? Well, this is the starting position. This is rest. This is the rest position. You would take it and you would displace it some distance, and then you would release it. When you release it, it is going to swing over here and
Yes, sir.
right? And then it's going to return back to its original position. That would be an oscillation. So understand what an oscillation is. I took it from rest and I displaced it. It swinged to the other side and then it would return back to its original position. That's oscillation, right? Another way to think about it is a fan. And all you know is a fan, like a Lasco fan or something. And I'm not sure if it have like a oscillate button, but like oscillate when it oscillating, it spins around. But doesn't it make like a full cycle? So like the fan would like move. Well, it would move 180 degrees and it would come back to its original position. That's what oscillation is. Basically, you're taking something and you're moving it away from the rest position, and then it returns back to the exact same position. That's oscillation. So it's like a whole cycle. Now, if you have one oscillation, you'd call that a pulse. If you have a series of oscillations, you call that a progressing wave. So waves that require a medium to be transferred are called mechanical waves. So based on that just now, could you all give me an example of a type of wave that would be mechanical? What waves can you think of require a medium to be transferred? And when I say a medium, I'm talking about like a wooden block or like some material. Some material. Adil, could you think of any waves that require a material to be transferred?
Uh, I know about that one too.
All right. When you go to them, if you're passing by like a big DJ truck, right?
Yeah,
Talk to me. Can you feel can you feel the vibrations? Can you feel the physical vibrations? Can you feel the wall shaking?
yeah,
Right. So in other words, the sound waves is traveling through the air and is passing through your body. Um, and you are hearing it because the sound waves actually vibrate the molecules in the air. So how are sound waves propagated? So for you to hear sound, do you know how that process goes? Do you know how you
no,
hear sound?
no,
All right, so the sound waves, a sound wave is created by a speaker moving back and forth. So it's actually moving air. It is moving air. Air is the medium. And when the speaker moves the air in and out, that reaches your ears, and in your ear it have like a very thin diaphragm. So when the vibrations from the speaker hits your ears, it's going to cause the eardrum to move back and forth, and that vibration is actually how you hear. So a sound wave, do you understand that a sound wave, it needs to pass through something. It needs to vibrate some molecules in order for you to hear. So when you hear a sound wave, do you understand that it actually vibrating the eardrum in your ears? Do you understand that?
yes, yeah,
Right. So that is something that is an example of a mechanical wave. Another example I could give you was the same example I gave Zachary. If you took your ears and you place it against the wall, or you place it against a wooden desk, if you hit the wall, would you hear the sound?
yeah,
Yeah, so in that instance, the sound wave is propagating through the solid. So when I talk about mechanical waves, I'm referring to waves that need a medium or a material to pass through, to be propagated, to be created. It needs to pass through something for you to hear it. So if that's the case, Adil, do you think you'd be able to hear somebody screaming in space?
no,
No, because space is a vacuum, right? The molecules in space, they don't move, right? The vibrations will not spread in space because it's vacuum. All right. Now, Adil, let's look at the second type of wave. So waves that could travel through a vacuum are classified as electromagnetic. Talk to me, Adil. Um, for instance, the visible spectrum light waves. Do you think light waves? Do you think light waves could travel in space?
Mm,
Think
I,
about it logically before you say anything. Light waves.
I don't think so.
All right. I have a counter argument. Can we see the sun?
Yes.
Where's the sun?
Or in space.
Right. So,
Mhm.
doesn't that mean the light waves passing through space and making it to Earth?
Yeah.
Yeah, so they could travel in a vacuum, they could travel in space. So, the visible light is actually on the electromagnetic spectrum. That would be classified as an electromagnetic wave. Because it doesn't. Okay, do you think light vibrates?
No.
No, that's not what light does do. Um, Nabil, if I shine light on a piece of wood, would the wood vibrate?
No.
No, does the light cause any movement?
No.
When you hear of mechanical and you think of movement like mechanical,
Yeah.
right? So do you think a light wave is a mechanical wave?
Nope.
No, because the light wave doesn't cause any movement. Yeah. Right. So I hope everybody understands that. So there are two types of waves you need to be familiar with: mechanical waves and electromagnetic waves. So you guys could copy this down. So mechanical and electromagnetic. Right. So we need to look at features of a wave. Right. So Jadon, let me know if you're there.
Yes, sir.
Okay, great. So do you all think you need some time to copy that down? This part over here? Let me know.
Yes, sir.
Yeah? Okay, take some time. I'll copy that down quickly. Right, so let me give you all a good definition that I vouch for a wave. So let me think of a good definition. Are they hearing anything in the background?
No, sir.
Okay, good. Right, so let me give you all a good definition that I personally vouch for. Right, so a wave is a means of transferring energy Right, so please copy down this definition for a wave. Right, so a wave is a means of transferring energy through a medium or space without the net transfer of matter. And when I say space, I'm referring to a vacuum, right? Nikolai, you into car audio one thing, right?
Huh?
You're into car audio one thing, right?
Of course. What do you
Right.
mean?
So I want you to understand. First of all, do you understand that a sound wave is a mechanical wave because it actually propagates through a medium and it actually causes movement? Do you
But I
understand that?
understand that now.
So because think about it, sound waves. Doesn't sound waves actively push and pull air in and out? Think about it.
Yeah.
The speaker
How the speaker
actually,
does work.
right, because the speaker displaces air and causes the molecules in the air to vibrate, and your ears actually picks up on that vibration. So do you understand that like 100% that a sound wave is a mechanical wave? Great.
Yeah, I understand that.
If there's no molecules to be vibrated, will the sound wave propagate?
Nope.
No. So in other words, you can't hear audio in space. Right? Good. Happy that you understand that. The next thing I want you to understand is you're seeing how they're saying you're transferring energy without the net transfer of matter. That part might sound a bit confusing because what do you mean without the net transfer of matter? That might be a bit confusing.
It
Yeah.
really is.
You ever took you ever took something and placed it in front of a port of a speaker?
Yeah.
Okay. You probably notice that the speaker pushes it and pulls it in.
Yeah, especially if you take a little cloth or so and put it by the pot.
Right. Right. Notice the behavior, right? What does it do? It pushes it out and then it does what to it?
It pulls it back in.
Right. So is it transferring the matter or is it just causing it to oscillate?
It oscillating.
Yeah. So it's not transferring the matter, it is just causing it to oscillate. So I'll be understanding now. If it was transferring the matter, then the cloth it would keep moving forward, 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 forward. But as you can see, with a speaker, it moves out and then it goes back in. It moves out, it goes back in. It's not transferring it forward or backwards. It's causing it to oscillate. You understand that now?
Yeah, I understand that.
Yeah, so that's why I'm saying it does not transfer matter. It's not transferring the matter, it's just causing the particles, the molecules, to vibrate. It's causing it to vibrate about a specific point, back and forth, to transfer the energy. It's not causing them to move like forward or backward consistently. Because Nikolai, if I say I'm transferring matter, doesn't that mean I'm taking it from one position and carrying it to the other position and leaving it there? I transferred
Yes.
it. But with the speaker, is it really transferring it or is it just causing it to move about the same position?
Move about the same position.
Exactly. So I hope I demystify the confusion there. Because when you read it, that part confusing, I understand. Right. Okay, I need to explain that part to some other people. I should have a video of me with a speaker. Let me see if I find it. With the speaker causing the paper to move in and out. See if I find
I'm
it.
concerned by the fact you have all these videos on standby.
My phone is just wait, I'll find it. I'll find it. Right, let me send it. Alright, so everybody here, I want you all to look at the video. Is the sound wave pushing the paper outwards? Like, is it transferring it? Is it moving it to a new position? Or is the paper just moving back and forth in the same position? Look at our video and tell me what is happening to the paper. Is it being moved to a new location or is it just oscillating back in and out?
Oscillating.
Yes, Shana, just see now like the paper moving in and out, right?
Yes, sir.
It not moving anywhere else. It just oscillating about the equilibrium position, the rest position. Like the same thing with the pendulum I told you. So like when you pull the pendulum and you put it you displace it, it's gonna move, and it's gonna land back at its rest position. Same thing with the paper.
Yes, sir.
Jadon, you look at the video and tell me, is the paper
Yes, sir. It's oscillating.
Right, and you're seeing it for yourself, right? They're moving in and out, in and out, in and
Yeah.
out. Right. If I stop playing the music, would the people have reached to the other side of the room? Or will the people still be in my hand?
It'll still be in your hand.
Exactly. And if I let go of the paper, it's gonna it's just gonna be in and out. It's not going to move anywhere of significance. It's gonna move in and out. I wouldn't want that though because it would be sucked in. Think about it like this, Jaden. If I let go of the paper, the speaker, when the speaker pushes in, it's gonna suck in the paper, and when it pushes out, it's gonna push out the paper. But I don't want the paper to go inside this box, right? That would be inconvenient. But the point is, the paper isn't being transferred. There's no transfer of matter. I want you to think of the paper as the matter, right? There's no transfer of matter. It's just moving in and out. It's oscillating about its quote unquote equilibrium position. Um, Danelle, look at the group chat and let me know if you understand what I mean by without the net transfer of matter. Because that's the only confusing part in this. Drew.
Um, so I understand the video,
Mm-hmm.
but I think if you don't mind, if you could go over the term net transfer.
Okay. So, Danelle, the paper, as you saw, the paper is being pulled in, and then what's happening to it? It's going in and then it's going
Out.
right. So when we talk about net, we're talking about total actually. We're talking about the total transfer.
Okay.
So if
Okay.
imagine it moves in by 5, right? So we could call that say -5, and then it pushes out with 5. What is the net transfer there? So it moved in by 5, so -5, and it moved out by 5. What's the net transfer there? Total.
0.
0. Yeah. And that would correspond to no transfer of matter. So without the transfer of matter. So
Okay. Thank you.
no problem. So it really not being transferred anywhere because it's just oscillating about the rest position. Like if I stop playing music, the speaker will settle. I mean the paper, it will settle in the rest position. But as soon as I play music, it's going to move in and out. And it's gonna oscillate about the middle point. Do we
Okay.
understand? You sure you understand that, right?
Yes, I do.
Okay. Jiran, Adil, Nabil, Nikolai, Shina,
Yes, sir.
Karina.
Yes, sir.
Yes, sir.
Okay, so like you see how Janelle told me she was confused about nets? That's good. I thought other people would be confused about that, but I didn't hear anybody. Net just means total. And if the speaker is being displaced 5 to the right, we can say -5. And then if it being displaced to the left, we +5. So Adil, if I add 5 and -5, what are you gonna get? Talk to my Adil. 5 and
Zero.
-5. Right. So did it transfer matter?
Yeah.
No, it didn't
No.
transfer matter. If it's 0, it would not transfer.
No. Yeah.
Yeah. However, imagine if I push something 7 to the left and then I push it to the right with 2. What is the net transfer there? So I push it 7 spaces to the left and then I push it 2 spaces to the right. What's the net transfer over there?
5 to the left.
5 to the left, right? So there was transfer of matter there. But over here, there wasn't. Yeah. Because Nikolai, doesn't the speaker, and you know the term X max? Nikolai, you know about that?
Yeah.
X max, right?
Yeah, I think I get that.
So that corresponds to the maximum travel distance of the speaker. So wouldn't the speaker move out and move in by the same distance?
Yeah.
Yeah. So there's really no net transfer of matter. The air molecules are just vibrating back and forth. That's all. That is literally all. And in doing that, it's transferring energy. Guys, I need to know if all are confused, eh? Cause like I don't want you all to be confused and you're not telling me. Danelle, I see you raise your hand, talk to me.
Yes, sir. So as you explained the paper example, that would be considered electromagnetic.
Nah, that's not electromagnetic. All sound waves are
Or that,
mechanical waves.
okay.
Yeah. It's easier to explain with mechanical waves because I feel like we could visualize that. Like, electromagnetic is a bit more abstract, but it's the same principle. Then now, mechanical waves you actually vibrating molecules, like there's physical movement involved, there's actual movement. Think about it like this, now.
Oh,
If you take your ears and you put it against a wall and you hit the wall,
mm-hmm.
wouldn't the vibration that you cause be transferred through the solid to your ears?
Yes, it would.
So sound waves is an example of a mechanical wave because mechanical waves require a medium to be transferred. So when I say a medium, I'm talking about a material. So
Okay.
in other words, the molecules in the material, they need to vibrate to transfer the sound wave. Yeah.
Oh, I understand. Okay.
If if there if there are no molecules to vibrate, will the sound wave be propagated? Propagated is a way of saying transferred.
Oh, no, it wouldn't.
Wouldn't say, would you be able to hear somebody screaming in space?
No.
No. That can't be depressing. Guys, imagine being an astronaut and dying in space. Nobody would hear you screaming. That's crazy. That's sad way to go out. Right? And electromagnetic waves. Then now, an example of an electromagnetic wave is UV vis. So like um ultraviolet, visible light, radio waves. All these are electromagnetic waves. Talk to me.
Without using a medium.
Exactly. So let me think about
Okay.
this, right? A good one is radio waves. Guys, how will you think all the radio does work? How will you think the radio does work?
A
I
radio,
think
as
it's
in like,
Radio waves.
Right. Yeah. So the radio waves would travel through the air and it would be picked up by a radio's antenna. Now, if radio waves was a mechanical wave, wouldn't it be very concerning? Like, think about it. If it was a if a radio wave was a mechanical wave, and you'd have feel first of all, do and radio waves travel kind of far? Think about it. Radio waves. For you to be able to go nearly anywhere in Trinidad and pick up a radio signal, and radio waves must travel like a decent distance. Think about it. Then now, think about it, right? You could go anywhere in Trinidad and you could probably you could probably open the antenna for your radio and she'd be able to pick up on some signal. Twin.
I think so, yes. Yes.
Right. Because our radio does pick up radio waves, right? Think of your TV. A TV is an even simpler example. And your TV does get signal
Yeah.
from right. All of that has to do with radio waves. So the radio waves are traveling through the air. The radio waves are traveling through the air. And it's reaching your television. Do you feel the radio waves? Does your radio wave vibrate anything?
No.
No. Drew, you just feel the radio waves passing through the air? You just feel the Wi-Fi signals passing through the air? Guys, or they just feel the Wi-Fi signals passing
No.
through the air? Yes or no?
no, sir.
No. Jadon, do you feel light passing through the air?
No, sir.
I'm talking about light. I'm not talking about ultraviolets. You will feel heat. Just pure light. You wouldn't. Long
Nah,
story short, those type of waves are electromagnetic waves in nature. They rely on electromagnetism. It's a different kind of properties as opposed to mechanical, which involves movement, right? And they don't need a medium or a material to be transferred to. In other words, they don't need vibrations. Then they aren't propagated by vibrating molecules back and forth. So there's no physical movement. You can't really feel anything. Do we understand the difference between mechanical and electromagnetic?
Yes, sir.
Okay, we sure, right? Like, are we 100% sure? Ambika. Is Ambika here?
Yeah.
All right, Ambika. Do you think X-rays be a mechanical wave or electromagnetic wave?
Isn't it an EM wave?
Yeah, it's a EM wave. Think about an X-ray. Do you feel an X-ray actively? Well, have you ever gotten an X-ray before?
No.
No? Okay. An easy example is radio waves. How you feel like, or even an even simpler one is Wi-Fi. Isn't Wi-Fi wireless?
Yeah.
Yeah, do you feel the Wi-Fi waves passing? Can you even see the Wi-Fi waves? Can you
No.
can you feel the Wi-Fi waves?
No.
You can't, right? That's traveling through the air. Do you think it needs to vibrate molecules to be transmitted, or do you think it
No,
just
it doesn't.
it doesn't, right? Otherwise you'd have feel something. Right. So mechanical waves involve physical movement, the vibration of molecules. Electromagnetic waves don't do that. They could travel through a vacuum. They don't need to vibrate molecules to be transmitted. Right. Good. So I'm going to take it that everybody has mechanical waves and electromagnetic waves copied down, as well as the definition of a wave.
Yes, sir.
Okay, good. So now now we're going to look at features of a wave. So I'm going to leave in phase last. Feel that's the most abstract one to understand. Nikolai, you ever wire speakers out of phase and hear with a song?
Yeah, that thing is song is total. It's like can't push.
Exactly. That's because the sound waves are opposing each other. And so when one speaker is moving in, the other one is moving out. And so they cancel off. That's why they sound so horrible. Right? So Nikolai, just by explaining that, you kind of have a basic intuitive idea about it. Because if the speakers are in phase, they are moving they're moving simultaneously. Like when one is moving in, the other one is moving in as well. When one is moving out, the other one is moving out. So in other words, their sound waves would combine. We call that constructive interference. Make sense?
Yeah, that makes sense.
So they come like one big speaker because all the speakers vibrating at the same rates and the in phase is synchronized. So they are contributing to the vibration, the type of vibration. So it would be amplified. So for those of you guys that are not so into speakers, this one might be a bit hard to understand. But I will still try to explain it. But anyways, let me look at these ones for now. Wavelength, amplitude, frequency, and period. These are the simplest to understand. So, Karina, I would like you to read period for me.
Period. Time taken for a wave's complete oscillation, measured in seconds.
Right. So, Karina, do you know what an oscillation is? Talk to me.
Yes. That's when an object moves 180 degrees from origin and moves back to origin.
Yeah, I'll take that. That's fine. That's fine. You can see it over here. Watch. So we starting from the resting position. We move up, reach back the rest, go down, reach back the rest. That would be a full oscillation. Full oscillation over here. Then you have another full oscillation over here. Then you have another full oscillation over there. Do we understand that? Do we understand what an oscillation is?
Yeah.
Okay. Could somebody tell me how much oscillations you would have here?
2.
What about the rest of you guys? Can you all see the two oscillations?
Yes, sir.
Yeah? Okay, great. Let me make my own notes on this. I prefer to do that. I prefer to do a lot more. We will use these examples to actually try to understand what the heck is going on. So guys, do you understand the difference between say like a speaker and a fan? Because like if we're talking about a fan, right? A fan blows air. It always blows air in one direction, yeah? Like a fan. Think about it. A fan. Isn't that what a fan does? Like a fan just blows air in one direction. Guys? Nabil, you there? Why everybody so dead today? I don't know what's going on. Right now, I feeling like this. I feel like I want to just, you know, don't know why everybody's so quiet. Zachary, why are you so quiet today? Are they even hearing me?
Yes, sir.
Yes,
I'm feeling bad, the silence.
Yeah, like I was hearing crickets chirping and all kind of thing just now, bro. Wow. Like, you hear what I was saying, right? A fan. What does a fan do? Like a Alaska fan or something. What does it do? What does a fan do?
They actually function of a fan?
Yeah, what does a fan do? Like real, I promise it's not a trick question. Like real simple.
Blow
It blows air, right? So if I put a piece of paper in front of the fan, what happens to the piece of paper?
air. It'll fly away.
It'll fly away, but if I put a piece of paper by a speaker, would it fly away or would it just move back and forth?
It'll move back and forth.
Right? So I really hope all you understand that example where I say it does not transfer matter, it just causes it to oscillate. I can't stress that enough. So let's look at the key things you need to understand when we're talking about a wave. Number one, you need to know what an oscillation is. Right? You need to know what you need to know what a wavelength is. Wavelength. You need to know what amplitude is. You need to know what a period is. You need to know what frequency is. All right. Do you all understand what an oscillation is visually?
Yes, sir.
Or what the rest of you guys? Is there anybody here that does not understand oscillation? So like an oscillation is just repetitive motion, that's all. So like something just keeps repeating itself. That's oscillation, right? Okay, wavelength, right? Length of one. What do you think we measure wavelength in? Wavelength. Length. What do you think I measure wavelength in? Somebody take a guess.
Meters.
Yeah, meters, right? About right there. Great. Measure this in meters. Does anybody have an idea as to what amplitude is? Right. So I'll give you all a I'll tell you what it is, right? So amplitude is the maximum displacement. So like Nikolai, amplitude, if we're talking about in terms of our speaker, amplitude would be like the maximum distance the speaker could travel. So maximum displacement all right, period. It's just simply the time it takes, time taken. This is just simply the time taken for one complete oscillation. Right? And frequency is just simply the amount of oscillations in 1 second. The amount of oscillations per second. Right? Does anybody know what I'd measure amplitude in? Does anybody know what I'll measure amplitude in?
Seconds.
Meters.
Nah, I'll measure amplitude in meters. Right?
Yeah, I just said that.
Say that again.
I just said meters.
I could have swear here seconds or something. Somebody just said that. Right? Period. If period is the time taken, what is the SI unit for time?
Seconds.
Seconds, right? Okay, frequency, y'all might know this one. Nikolai, yeah, what do you measure frequency in? You should know this. If you're sensing the speakers, should have an
Yes,
idea.
frequency in hertz.
Exactly, frequency is measured in hertz. And it just simply corresponds to how much time. Okay, if we're talking about speakers, right, Nikolai? Let me just say you have 5 hertz. That would mean that the speaker is moving in and out 5 times in 1 second. Make sense?
Yeah.
Right. So frequency is just simply the amount of oscillations you have in 1 second. In 1 second. Great. Is everybody okay with those terms? Yeah or no?
Yes, sir.
Yeah.
I'd bet. So the symbol for period is denoted by T, right? Frequency is denoted by common F. And the formula for frequency is just 1 over the period. So 1 over T. Right? Right? The amplitude is just simply A. Right? Wavelength is this symbol over here, which is lambda. Yeah. So make sure you have this copy down and we'll look at some examples. Right, so when you have this locked in, let me know. We'll be ready to do some questions. I promise it's not that hard. Right? And the formula that you need to be familiar with, right? You need to be familiar with this formula. V is equal to F lambda. And what exactly does V stand for? V stands for the velocity of the wave. So guys, if we were talking about a sound wave, do you all know what the velocity of a sound wave is? Do you know the speed of a sound wave? Does anybody know the speed of a sound wave? Does anybody know? Drew, do you know what the speed of sound is? Okay, everybody, real quiet. It's 300 and something. Right, so it's 343 meters per second. That's speed of sound. So the main formula that you guys will need to be familiar with is V is equal to F lambda. So the velocity of a wave, right, is just the frequency multiplied by the wavelength. And that's going to tell you how fast the wave is moving with respect to time. So it's velocity, right? Right, so let me know when you guys have this down. And the main types of graphs you all will you'll need to familiarize yourself with. You'll need to familiarize yourself with a displacement, and displacement is measured in meters. So a displacement distance graph right, and you need to familiarize yourself with a displacement time graph. Right, so those are the two types of graphs you need to be acquainted with at this level. So Ambika, as soon as you have everything unlocked, Lamona, right? As soon as you have everything copied down, let me know. Okay, Ambika, so you're on mute just now, but in here. Talk to me.
I have everything.
Okay, what about the rest of you guys?
I'm on the last two displacements.
All right, so those are the different types of graphs you need to be familiar with, right? So a displacement distance graph and a displacement time graph.
All right, so no problem.
Right. 1 second. Right, do like this instead. This is how this come most of the time. So you would see displacement distance graph like that, or displacement time graph like that. Yeah. But just note, in the first graph, you're gonna have displacement on your y-axis, and you're gonna have distance on your x-axis. For the other type of graph, you're gonna have displacement on the y-axis and time on the x-axis. So as soon as you have that down, let me know. Nikolai, have everything copied on? Nabil, Chidan, let me know, guys.
Yes, sir.
Yeah,
Yes,
no.
sir, I haven't copied down.
All right. Well, let's do a question. All right. Let's do a question. Okay, in this type of question, what kind of graph do we have? Look at the axes, and it will tell you. What kind of graph do we have?
A displacement graph.
Not just a displacement graph. We have a displacement. We have a displacement time graph. What's in? What's in displacement time? We have a displacement distance graph. Look at the axes. The axes will tell you, watch, displacement distance graph. So that's the type of graph given.
Okay.
Okay. Part B, state its amplitude A and its wavelength. So, guys, this will be my resting position, my equilibrium position, and everything else will be a displacement. So look at the graph and tell me, from the graph, what is the maximum displacement? So if this is the equilibrium position, what, by looking at the graph, what do you think is the maximum displacement from that? How much meters? Right. So yeah. All right. Yeah. Adele there.
Yes, sir.
So Adele, over here, the wave would have been at the equilibrium position and it's moving out, and this will be the maximum. So the maximum will be how much meters?
Does
How much meters?
0.5.
Nah, watch that again. So it start from 0, it displace, and it reach a maximum. What's our maximum?
1.
Right. Then it would decrease, reach back to 0. Then it would decrease, it would reach its maximum over here, which is what?
-1.
Right? Then it would go back to its rest position. So the maximum displacement is just 1. So guys, the amplitude is literally just the maximum displacement with respect to the equilibrium position, which is the distance axis here. So let me know if you guys understand that. Do you all understand why I'm going to say the answer is 1?
Just to run that back one more time, there, please.
All right, so Nikolai, we have a graph here showing how the wave is being displaced with respect to distance. So we're going to start off here, and the wave is going to be displaced. So when you think of displaced, think of moving it, right? We're moving the wave. Think of a speaker. So maybe in this part, the speaker might be moving out, 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 out. So what is its maximum displacement? They can move outwards,
1.
right? And then it's at a decrease. The speaker now moving in. Where's the maximum? The speaker could move in.
-1.
Well, not -1, eh? Be 1. But the reason why we say -1 is to indicate direction. If it is moving in, then its opposites are moving out. So it's still moving in by 1 meter. It's just -1 to indicate the direction, right? And then the speaker would return to its original position. Let me know if you understand that.
Yeah, understand that now.
Right. So displacement is just the maximum. I mean, the amplitude is just the maximum displacement. So what is the maximum displacement? 1. See now, right? It's 1. 0 to 1. Let me know if you understand that.
Yeah, understand that.
Right? So the amplitude, I'll make a little mistake here. Amplitude is supposed to be a common A, right? Amplitude is common A. So make that change. So, Nikolai, the amplitude here is just simply going to be 1 meter. Let me know if you're okay with that.
Yeah.
Right. Part 2 now. They are asking us to figure out the wavelength. Does anybody remember the definition for the wavelength? It's simpler than you think. So, wavelength. It kind of sounds like the length of the wave. What is the length of one full oscillation here? So, does everybody understand that this is one full oscillation? Yes or no?
Yes.
Right? What is the distance? What is the distance for one full oscillation?
2 meters.
Yes. So the wavelength is just 2 meters. So then now, do you understand that the wavelength is literally just the length of the wave? Okay, I don't think the null is here. All right. Right. Ambika, do you understand that wavelength is just the length of the wave?
Yeah.
Right. And in this case, the length of the wave for one full oscillation is 2 meters. So my wavelength is 2 meters. Zachary, do you understand what wavelength is? Lambda? Or nah? Can I hear Zachary? Nabil. Talk to me if I don't know if you understand. I don't know if you understand what a wavelength is.
Yes, sir.
Okay. So Nabil, how would this be then? Would that be like a quarter of my wavelength, half my wavelength? What do you think that would be?
Half?
Yeah, that'll be half the wavelength. Right? Great. So Nikolai, I want you to help me with part C. This might be a bit tricky. So Nikolai, in part C, they're telling us the what? What are they giving us? Up front, what are they giving us?
They're giving us the frequency is 50 hertz.
Let me mark that down. So the frequency is 50 hertz, right? And they want us to calculate its periodic time, t. Its periodic time, t. Do you know any formulas that involve frequency and period? Talk to me. Are there any formulas that you know of involving frequency and period?
Yeah.
Let me go back, check it out. Are there any formulas you see in here involving frequency and period?
Yeah, I think so.
What formula involving frequency and period?
I think that is F equal I over T.
As 1 over t. 1 over t.
Oh,
Yes. So the formula that involves frequency and time period is F is equal to 1 all over t. Are you all okay with that? So here how we figuring out which formula to use, right? So Nikolai, they're telling us what the frequency is. So immediately you should be asking yourself, what formulas have frequency in them? The only formulas I know that have frequency in them is F is equal to 1 over T that has frequency in it. And is there another formula that involves frequency? Is there another formula that has frequency in it? Let me know.
Yeah, the one with velocity.
Right? And that formula looks like this. V is equal to
F.
right?
Well,
And
high
that's
frequency
lambda.
and wavelength.
Right? That symbol is lambda. Okay. Now, if these are the two formulas that have frequency in them, talk to me. In the first part, they want us to find for periodic time. Which formula contains frequency and periodic time in it? 1 or 2?
1.
Do you understand why I chose 1?
Yeah.
And in part 2, they want us to find the velocity. What formula do you think I'll use there?
2.
2, exactly. Exactly. That's all I wanted to be thinking in the physics exam. Right? Run through all the options in your head. So Nikolai, let's do some substitution now. So I know that F is 50, so I'm going to write 50, and 50 is going to be equal to 1 all over T. So I need to find for T. What do you want to do next? How am I going to find for T?
Make T the subject of the equation.
How am I going to do that?
Multiply by T by 50.
Nah. Let me show you a trick you could do, right? It's a very cool trick. Anytime you have a fraction on either side of the equation, so watch this. We have 50 is equal to 1 over T, right? Another way I could write that is 50 over 1 is equal to 1 over T. Yeah? Tell me if you're confused.
Nah, I understand.
So watch this, right? If I wanted to find for T, do you understand that T is the same thing as T over 1?
Yeah.
You're sure you understand that?
Yeah.
Okay, so look at what I could do, right? For me to find for T, this is all I had to do. I just had to flip both sides. So 1 over 50 is just simply equal to 1 over T. I mean, T over 1. And T over 1 is what? What is T over 1?
T over 1.
Yeah, T over 1.
T over 1 is the
T,
period over 1.
which is T.
Yeah.
Yeah, so just so that we found for the answer, T. Let me run that back one more time. So we had 50 is equal to 1 over T. And we are trying to make T the subject of the formula. So we have 1 over T. What is the reciprocal of 1 over T?
1.
Nah, the reciprocal will be T over 1. Reciprocal just means to flip. So T over 1 and T over 1 would just be equal to T. T over 1 is T, right? So if I want to get my answer, I just have to find the reciprocal on both sides. So 50 is the same thing as 50 over 1, right? And I want to make T the subject. So I'm going to flip both sides. If I flip both sides, 1 over T is going to turn to T over 1, which is just T. And if I flip 50 over 1, that's going to be 1 over 50. So could you tell me what 1 over 50 is, 2 decimal places?
Yeah.
What is 1 over 50?
Zero 0.02.
0.02 you get?
Yeah.
And that would be what? What are the units for period?
T.
Nah, remember,
Nah.
period is the amount of oscillations. What was I
That
saying?
will be
Wait, that's frequency. Frequency is the amount of oscillations in 1 second. Period is period is just simply the time it takes for one oscillation. Let me run that back one more time so you understand it. Frequency is how much wavelengths, what's in? Frequency is how much time the wave is oscillating in 1 second, right? So in your case, how much time is the speaker moving in and out in 1 second? So Nikolai, 50 would mean that the speaker is moving in and out 50 times in 1 second. Understand?
Yeah.
Right? The period is the time it's going to take for one oscillation. So in other words, the speaker is going to move in and out in 0.02 seconds. Make sense?
Yeah, it makes sense now.
Right, so period is just simply the time it takes for one oscillation. So if we're talking about time, the units is going to be seconds. So it takes 0.02 seconds for one oscillation. That is the period. Now that was not the only way you could do the question. If you wanted, you could cross multiply. And that would be, I could write 50 as 50 over 1. And if I cross multiply, that's going to be 50 by t is 50t. 1 by 1 is 1. And then you just divide both sides by 50 to find for 1t. And you get t is equal to 1 over 50. Both instances, they get the same answer, 1 over 50. Okay, first of all, is there anybody here that does not understand why I decided to use this formula? Talk to me. After this question, that'll be for class for today, right? But is there anybody that does not understand why I use that formula?
No, sir.
Right. I use that formula because they gave me frequency and they asked me for periodic time t. So I need a formula that has both frequency and time, periodic time in it. So F is equal to 1 over t. So frequency is 50. I don't know what my period is, so I leave that blank. One of my options is to reciprocate both sides. If I find the reciprocal on both sides, 1 over t turns to just t. So t is equal to 1 over 50, and I get my answer one time. You could also choose to cross multiply. 50 by t is 50t, 1 by 1 is 1. From here, just divide both sides by 50, and you get your answer. Nikolai, are you confused?
Nah.
And talk to me. Remind me, what does period mean? What does period tell me?
Period is the amount of seconds of oscillation.
Right, is the time it takes for one oscillation. Right? Good. Let's do the last question now, part 2. In part 2, we need to find the velocity. So v is equal to f lambda. What is the frequency?
50
What is the wavelength?
2 meters.
Right, so 50 by 2 is?
100.
And what is the units for velocity?
I honestly can't remember.
Right, so velocity is the same thing as speed, right? More or less. It's just that it's just that velocity is a vector quantity for speed. But it's the same units. Do you remember the units for speed?
Yeah, in 30 seconds or not?
Nah, let me show you a way to figure this out, right? If you're driving a car, right, it is give you speed and what? What are the units for that?
Kilometers
Just kilometers?
or miles.
Nah, it's not. It will be like 100 kilometers per hour. It's kilometers per hour. But in this case, distance is in kilometers and time is in hours. But in physics, we need to use SI units. So Nikolai, what is the SI unit for distance? Is it kilometers or meters?
Meters.
Right, and in our car is kilometers per hour. But in physics, we need to use SI units. Again, what is the SI unit for time? Is it hours or seconds?
Seconds.
Right, so the unit for velocity, which is the same thing as speed, is meters per second. Yeah. So this is how fast the wave will travel, right, in 1 second. So in 1 second, this sound, well, whatever wave this is, it's going to travel 100 meters in 1 second. That is the speed or the velocity of the wave. Is there anybody here that didn't understand why I did at all? Talk to me, guys. I'm gonna know.
No, sir.
All right, Ambika, Karina, Drew, Nabil, Zachary, Jiran, Adil, talk to me. Let me know what's going on. Let me know what's going on, guys.
Yes, I understand.
Okay.
Yes, sir. Mm.
All right, so let me give you all some homework, right? No, we had to I had to give you some homework. So like, it's not gonna be much. So you had that question and you have this question as well. Quickly, somebody tell me what kind of graph this is. What kind of graph is that? Tell me fast. What kind of graph is that?
Displacement and time.
Displacement time graph. Excellent. So for this question, probably call it number 4. I want you to tell me state the type. So state/calculate the following. So number 1, tell me what the amplitude is. Number 2, tell me what the period is. So tell me what t is. Number 3, tell me what the frequency is. Number 4, if I tell you that the velocity is equal to 343 meters per second, find the wavelength. Yeah, so that's your homework here. So like, somebody take a screenshot of this and put it in chat one time fast. Put any screenshot. Put that in the chat. Right? Did somebody take a screenshot and put it in chat? Did anybody take a screenshot? Okay, big up yourself, Karina.
Yes, sir.
Right?
Okay.
Take a screenshot of this and put it in chat too. Wait, 1 second. Yeah. So if I ask like quickly, what is wavelength? What you tell me? Wavelength is what? What is wavelength?
Length of a full acceleration or oscillation.
Right, length of a full oscillation. What is periodic time?
The time taken for one complete oscillation.
What is frequency?
the amount of oscillations per second.
Excellent. I'll have it on lock, right? It's amplitude.
The
Maximum
maximum
displacement from the
From the what?
equilibrium position.
Right, equilibrium, which means rest position. Great. So, where's the equilibrium? What's in? What is the amplitude for this? Tell me fast. What's the amplitude for this? Just by looking at it, what's the amplitude? Quick, guys. What's the amplitude?
0.06.
Right, 0.06. What is the wavelength? No, you can't figure that out just so. Let me explain why I can't figure out wavelength. You can't figure out wavelength for this graph because the x-axis is not displacement, or is not distance. You need, for you to figure out wavelength, remember wavelength is the distance for one full oscillation, but if you look at this graph, the x-axis measures time. It does not measure distance. So you can't read what the wavelength is from this graph. That's why in part 4 I told you to find the wavelength given that v is equal to 343. Okay, what about the periodic time? What is the periodic time for this? Somebody tell me, what is the periodic time? T. Anybody tell me fast. Periodic time.
0.02.
0.02, right? Because that's the time it takes for one full oscillation. Right? So I think you'll have it. You shouldn't have any problems with these questions. Right? Cool. So yeah, guys, I hope all you have a good Saturday. Right? I will see you all next week. Later, guys. Take care.
Yes, later.
Later.
Bye.
Bye.